Hi, my name is Naeem Turner-Bandele, and I'm a PhD candidate at Carnegie Mellon University. For the next several minutes, I will present the work I did with Pandey and Larry Pileggi on creating an inverter-based distributed generator model for distribution systems analysis. As we all know, solar photovoltaic devices connect our electric power grid via inverters that convert a DC input to an AC output. These devices, also known as inverter-based distributed generators, or IBDGs, and inverter-based resources, or IBR, are increasing in prevalence and penetration on the grid. An increased number of utilities are installing IBRs, and record amounts of generation have been installed on the distribution grid in the last year. Despite increased penetration and presence, modeling analysis of these devices and power systems has lagged. In power systems analysis, solar IBRs are primarily treated as negative PQ loads and modeled aggregately. With the trends of increasing solar IBR penetration expected to continue, it's crucial to resolve modeling issues. Otherwise, according to the North American Electric Reliability Corporation, this could result in unanticipated power flows and increased demand forecast errors. Our work sought to more comprehensively model inverter-based distributed generators by extending and refining inverter-based distributed generator models to reflect operational characteristics better and alleviate modeling issues. We work towards our objective of improving inverter-based resource models in the distribution system by primarily doing four things. First, rather than represent an inverter-based resource abstractly using a PQ or PV model, we derived an equivalent circuit of a three-phase current-controlled voltage source inverter in terms of its positive and negative sequence components. Next, we obtained nodal currents for the positive and negative sequences using KCL. Finally, we split the derived currents into their real and imaginary components to apply Newton-Raphson, which we use as the basis for our distribution system solver. With an equivalent circuit and nodal equations derived, we focus next on considering physical inverter limits. For our work, we derived the peak current for the flexible positive-negative sequence inverter-based resource control strategy, and then obtained an expression for the maximum reactive power given the current limits. This value was used in inverter volt-var control and ensures that the currents in all phases of a multi-phase inverter are always within bounds. The final component of the model was volt-var control. Voltage regulation is a crucial component of an inverter-based resource. Using three linear regions and a cubic spline, we represented and integrated the inverter's voltage regulation implicitly into our overall model. This implicit incorporation is different from other works which use outer loops to implement voltage regulation. You can see an example of the volt-var control curve implemented in Figure 1 here. After the implementation was complete, we validated the steady-state response of our IBDG model against synthetic data for a single node test case to ensure accuracy. As you can see here in Figure 2, we showed that using our IBDG model, the current magnitude difference from the ground truth or synthetic result is smaller than the current magnitude difference attained when using the GridLabD inverter model seen here in black. Upon validating our model, we decided to assess the possible improvements that one could attain when using a significant number of IBDGs in more extensive test feeders. For our experiment, we selected 3 PG&E feeders of varying complexities with differing levels of solar photovoltaics. We evaluated all 3 feeders with their different configurations using the IBDG model in our distribution system solver known as SugarD. We found that using the IBDG model in our solver resulted in a different voltage profile from the one attained using GridLabD. You can see this in the table below. A non-analytical model, such as the one in GridLabD, might tend to overestimate or underestimate nodal voltages and could result in high voltage imbalance. Moreover, the VDIF, or the voltage deviation from the nominal reported voltage, was smaller for 2 feeders using the IBDG model. To conclude, we've shown that using our IBDG model can ensure that results are closer to the grid's actual state. In the future, our work will focus on incorporating different types of inverter models and controls, as well as focus on characterizing and propagating uncertainty in inverter-based resource models, given that future distribution systems will be less deterministic and more probabilistic. Thank you for listening and taking an interest in our work.